Nuclear fission is a source of energy that has been around since the beginning of the universe. Scientists have identified sites in Africa that show fissioning has occurred naturally long before scientists duplicated the process in the laboratory. Fission means splitting into parts. It occurs when an atomic nucleus splits into two fragments, producing energy. Let's look at the steps that led to the discovery of fission. For scientists, the atom has been an ongoing challenge. What is an atom composed of? How do the particles that make up an atom relate to one another? What holds an atom together? Can atoms be broken apart? How can this knowledge benefit us? Experimenting with uranium, two German scientists, Otto Hahn and Fritz Strassmann, bombarded atoms of uranium with neutrons. Unexpectedly, they found that the nucleus of uranium sometimes fragmented into lighter nuclei and that energy was released. A neutron had struck a uranium atom's nucleus, which split in two, nuclear fission. The year was 1938. At the time, they didn't understand the importance of their work. Hahn told the story of his discovery to Lisa Meitner, a former co-worker who had fled Nazi Germany to Sweden. There, with her nephew Otto Frisch, the concept of nuclear fission, the splitting of an atom into two parts, was presented to the scientific community. Other scientists soon realized that if this splitting of the uranium atom could be sustained, a new source of energy would be the result. In 1942, an Italian scientist, Enrico Fermi, was the first person to produce a sustained nuclear reaction. In a crude atomic pile built under the stands at the University of Chicago football stadium, he proved that a chain reaction could be controlled. Others used his work to develop the atomic bomb during World War II. Fermi's work also made it possible to utilize the atom for peaceful purposes. In a nuclear power plant, the heat from the fission process is used to create steam, which powers electric generators. But not all atoms can readily fission. Let's take a closer look at fissioning as it occurs in uranium-235, the most common form of fuel used in nuclear power plants. The uranium-235 atoms are split into smaller atoms when hit by a neutron. When the atom splits, it releases heat, radiation, and 2 or 3 more neutrons, which under controlled conditions of a nuclear reactor, strike other uranium atoms, causing them to split, resulting in a chain reaction. But how does the neutron really cause the nucleus of a uranium-235 atom to split apart? Let's use a droplet of water to represent the nucleus of the uranium atom. Remember, the nucleus is composed of protons and neutrons that are being held together by the nuclear force of attraction between the protons and neutrons. This nuclear force of attraction is part of the binding energy that holds the atom together. The nuclear force is a short-range force, that is, it will weaken if particles are separated. During fissioning, a neutron enters the nucleus. The protons and neutrons in the nucleus start to vibrate, increasing the space between them, due to increased energy imparted from the incoming neutron. This vibration weakens the nuclear force, causes the nucleus to change from a spherical shape to an elliptical shape. This new shape of the nucleus disrupts its electrostatic balance. Electrostatic charge of repulsion between the protons starts to become stronger than the nuclear attracting force. The increase in repulsion force causes a further elongation of the nucleus to occur. Continued vibration and electrostatic repulsion causes the nucleus to further elongate into a dumbbell shape, with each end eventually developing an overall positive charge. Then the electrostatic charge of repulsion overcomes the nuclear force of attraction, causing the nucleus to split into 2 fragments, releasing energy and 2 or 3 neutrons in the process. Neutron-absorbing materials and moderators are used to control the rate of the chain reaction. Neutrons produced by fission travel at an incredibly high speed, approximately 36 million miles per hour. At this speed, the neutrons are not able to be absorbed by the nucleus. But if neutrons are slowed down to about 15 miles per hour, a sustained fission reaction can take place. Water acts as a good moderator, slowing down the speed of the neutrons as collisions with water molecules take away some of the neutron's energy. The fuel rod houses the fissioning uranium. Some of the neutrons released during fissioning must be absorbed to control the reaction. Neutron-absorbing materials such as control rods and boron actually remove neutrons so they cannot fission other uranium atoms. A reduction in number also controls the fissioning rate. The two fragments produced by fissioning are called fission products. Barium and krypton are the two most common fission products, although others are formed. The nuclei of these atoms are very unstable and give off energy, which we call radiation.